Okay, so we're going to be going over the review slides for Organic 1, Exam 1, stuff like that. So the test will be Wednesday, so good luck, stuff like that. So, okay, so these are going to be the free answer part questions on the exam, stuff like that. So these will be an example of all of them, stuff like that. So, okay, so first thing, right, so give electron state configuration for the for aluminum, right? So this is like the 1s2, you know, dot, dot, dot. Like that. So easiest way to do that, right? So is to come in here, take a look at the periodic table, right? So remember this is the S block, right? This is the right. So that's the P block, right? That's the D block, right? And down here that's the F block. But we're not going to get into that. But basically, all you have to do is you have to start walking your way across the periodic table. Okay, so we're gonna get to here. So right, that's so S block, right? So first one up, so 1s, right? There's two electrons in here. That's the weird one. Something like that. Next up, if you walk across, right? So it's 2s, right? There's two electrons in there. And then we're going to go over here. So the first orbital type we come to is the s. We start that with 1. The next orbital type we come to is p. So that actually starts with 2p. 2p. So like that. So and we have 1, 2, 3, 4, 5, 6. 6 going across. Okay? Now, if we were going through the 3D block, right? The first one we would come to, right? So it's the third type we come to. So that you start with 3D and then go across. That'd be 3D10. If you were down here, you actually start with the 4. If you had to go through the F block, it would be when you got to this point, it would be 4F, and then you go across. I believe it's 14. So like that. So okay, we're not gonna get that far because we're only going right there. So 2p6, and then back here 3s2, right? And then going here would be 3p1. Now, if you wanted to abbreviate it, right, and that's fine. I prefer this when you're just starting out. Go ahead and write it all out. But you come back here and go back to the previous noble gas. So in this case, it would be neon, right? And then you do everything after it. So it would be right. Neon would be 3s2, 3p1. Okay. So there you go. So I'll take either answer. So now you do the same thing if you want to do it with the arrows, right? So you have 1s2, so you go up down. Right? 2s2, up down. 3s or 2, it should be 2p, right? That's next, right? So there's 3 orbitals, and generally just out of habit, I'll go up, 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 down, 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 because that's how they get filled. Right? You do the ups and then you do the downs, right? Because they want to be individually before they want to be paired. Okay, so so we're here and then 3s, right? There's 2 of them. So there, and then 3p, right? So we have 1, right? So we'll just be an up, right? So, so let's say we went over a little bit farther for something like sulfur, right? So if we did sulfur, right, it would be neon, but the valence electrons, which is the important part, right? It would be 3s2, 3p, right? Count over 1, 2, 3, 4, right? So 3p4, right? So it would be 3s2. You get 2 of them. And then the 3p shell, right, you would go up, 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 down. Okay, you don't pair these guys up, right? There's, sulfur, right? It likes to have 2 lone pairs and 2 bonds, right? That's how it likes to be. It doesn't have 3 lone pairs and then missing, an electron out of an orbital, right? So that's what this likes. Okay, so it's not going to be any worse than this. Yep. Next up, hybridization, right? So remember the hybrid, right? So the hybrid equals, right? It equals bond sets plus lone pair sets, right? And that's going to give you how many letters you have to deal with, right? So you always start with S, and then you should add P's to get how many letters you need, right? So for this one, right? So how many bond sets does it have? Right, it has 1, 2. Right, it doesn't matter if it's a this is one of those few cases where a single, double, or triple bond all count equally, right? So it has 2 bond sets, right? 1, 2, right? It doesn't have any lone pairs, right? So it's 2. So we need 2 letters. So it's SP, right? So you start with S and then keep adding letters, right? So SP. So it'd be SP1. Although I guess if you put SP, that'd be fine. So with that, so for this one here, right? So with that, so what do you have, right? So you have 1, 2 bond sets, right? Right, and 2 sets of lone pairs, right? Right, so there's 4. So you're gonna need 4 letters, right? So it becomes SPPP, right, which becomes SP3. There you go. Now, if I were to point something like to that, right? So how many bond sets does it have? It actually has 4. Why? You'd say, oh wait, it only has 2. But remember, with skeletal structure, right? You don't have to draw in the carbon-hydrogen bonds. They're still there, right? But you don't have to draw them in, right? So there's actually 1, 2, 3, 4 bond sets on that carbon. No lone pairs, right? So it'd be 4, right? SPPP, right? So it's SP3. Right, so don't let the skeletal structure confuse you. There's still 4 bonds to that carbon. Right? They just all happen to be single bonds, so it's sp3. Okay, now for dipole moment, what you're looking for is the electronegativity of this. And I'm going to give you the numbers for this. You don't have to memorize them, but you can always just look at the periodic table if you don't remember what the numbers are. Right, and the more electronegative the atom, right, the closer it is to fluorine on the periodic table, right? So going across, right, so electronegativity going across is fluorine, oxygen, nitrogen, carbon, boron, right? So this is of these 5, right? Boron's least electronegative, but fluorine is the most, right? So and again going down, fluorine's going to be the most, acetine is going to be the least electronegative, going down. Okay, so you just have to look, right? So going across here, carbon-hydrogen bonds, those are considered just regular covalent bonds. Carbon-carbon bonds are covalent, right? Anything that bonds to itself is considered just a plain covalent, right? Because there's no difference between the 2. But for carbon and oxygen here, right? Right, so carbon and oxygen, right? So this is going to be slightly more negative, right? This is going to be slightly positive, right? So the arrow would go like that, okay? Because oxygen is going to be more electronegative, so the electrons are going to spend more time on it than down here on this carbon. Same goes with this, which doesn't matter if it's a double bond or single bond or triple bond or whatever. You're just looking at the difference between the atoms, right? So this one again is going to look like that, right? So those are the individual dipoles. Right, and so what happens for the overall dipole? It's going to be halfway in between, right? So this is going to be the overall dipole. It's going to go right in between, right? Stuff like that. So it's halfway between these 2. Okay. Now, if this was wrenched down here, so right, so if it's something like this, like that, right? Again, you're going to have the dipole here, right? But it's equal and opposite, so there's no overall. There's no overall dipole on carbon monoxide, right? Because the dipoles are pulling in equal and opposite directions, right? So the average it just cancels each other out. So there's no overall dipole. So there you go. So formal charge. So for formal charge, right? So the charge is equal to, right? It's equal to the valence electrons minus how many electrons now, right? And so what you do is you say, remember that each bond, right, has 2 electrons in it, right? And so what you do is you slice it in half, each bond in half, okay? So this oxygen, right, it still retains its lone pair, right? But then it gets 1 electron from each one of those bonds, right? So oxygen, right, you look at the periodic table, right? So how many valence electrons does it have? 1, 2, 1, 2, 3, 4, 5, 6. Right? So it has 6. And you subtract how many it has now, which is 1, 2, 3, 4, 5. Right? So therefore it's positive 1. Right? So how many valence electrons would it have from the periodic table minus how many electrons it has now? That's going to give you the formal charge. It could be 0, it could be whatever. Right? So there you go. Okay. Next up, resonance structure. Okay, so now remember, in order for you to be able to participate in the resonance structure, you have to satisfy one of the following. Right? You either need a charge, right? You either need a lone pair of electrons, right? Or you need a double bond. Or I guess triple bond would work too, but you know. Okay, if you satisfy one of those, right? You can participate. Okay, so all of these guys. So that has a charge. These two carbons are on. These two carbons are on double bonds. These two carbons are on double bonds. But this one has none, right? So this one only has single bonds. It doesn't have a charge. Doesn't have lone pairs. None of that stuff. So this guy, that one there, cannot participate in this. Now, I will give you a suggestion that when you're doing resonance structures, sometimes it's easier to go ahead and draw the hydrogens on the eligible atoms, just to make it. Try to see, get more sense. Okay. So usually, so usually start where the charge is. Okay. So like that, and you're trying to get whatever atom that is back to where it really wants to be. Okay. So right now, the carbon only has 4 bonds, or so 3 bonds, right, and it wants 4. So what it does is it can't talk to this guy. This guy can't participate. But what it can do is it can say, okay, talk to this carbon. Hey, let's move this double bond over to here to give you this structure. Right? Right? So if you move it over here, right? So now these two have their 4 bonds, right? Now this one here only has 3 bonds, right? So it bears the positive charge. Right? So now this guy needs to figure out a way to get its 4th bond, right? So it can go back here and talk to this guy, but it would just go back to this structure. So what it's going to do is it's going to talk to this carbon here and have it move those pi electrons over there. Right? So you end up with this structure. That. Okay, and so this one here, right? I have to draw that hydrogen. Okay, so it would, it might want to be able to talk to this carbon to make a 4th bond, but it can't, right? Because this one only has single bonds. So you're at the end of your line, so you're done. Something like that. So, and notice that there's a skipping effect here. You skip it here to go there. You skip it to go there. That's not uncommon in these resonance structures. Right? But you've gone to the end of your line, and you're done. So there you go. And the line of eligible atoms. So there you go. So okay, so for skeletal structures, right? So the first thing you do for these, right, is to go ahead and just get rid of any carbon-hydrogen bonds, right? Like that. And then where these carbons are, just go ahead and put dots. Right? And then O, H. 1, 2, 3, 4, 5. 1, 2, 5, right? And then there's this one here with don't forget include the lone pairs. Right? So here we go. And then just fill in the bonds, right? There you go. That's technically correct. Right? Now if you want to do like a sawtooth pattern, right? You would actually go 1, 2, right? 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Right? Off this one, there's a double bond O, lone pairs. Here, I forgot the lone pairs there. Lone pairs here and H, and there you go. Oh, and then the triple bond there, and there you go. Like that. So either one of these will work. Now, notice that I didn't get rid of that hydrogen there, right? Well, right? Because if it's hydrogen is not on a carbon, you still have to show it, right? But just the ones off the carbon. There you go. So don't forget the lone pairs in there. Okay, so naming of alkanes. Okay. Right, so here we go. So go ahead and put in the dots where all the carbons are. That, right? First things first, we got to check out the longest chain, right? So you might as well start with the horizontal, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's looking like this is going to be, that's going to be the main chain there. Okay, so this one here, so that main chain, right? It's C9, right? So that's no name. Okay, so we've taken care of those 9 carbons are taken care of with this no name. Okay, so now we're going to deal with these guys here. Okay, so we have a 1 carbon piece, so that's a methyl. Right, we don't count that one down there. That's part of the no name. It's part of the main chain. It's just a 1 carbon piece away. Right. Next up is a 2 carbon piece, right? So that's methyl. Right, and then another 1 carbon piece is methyl. Right. So here we go. So if we're going to, right, so we don't know which one is carbon 1. We may have suggested, but it's usually good to go ahead and try both ways because sometimes you can get fooled. Right, so if we're going to say this is carbon 1, so we 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. So that would mean this methyl, right, is off of 3. That's ethyl's off of 4, and this methyl is off of carbon 5, right? So if we're going to do carbon 1 over here, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that would mean this one again is off of 5. This one's off of 6, and this one's off of 7, if you go with the blue numbers, right? So you add them up, right? So this is 9, this is 12, right? So this is 12, 18, right? So you pick the number that adds up to the least, and there you go. Okay, so which comes first, ethyl or methyl? Well, we're going to go alphabetically, so the ethyls come first. Okay, so it'd be 4 ethyl. Okay. Okay, so we have two methyls, right? So we're going to say di, right? We're going to dash 3, 5, right? So whenever you have between a number and a letter, or letter and number, you put a dash. If you're separating out numbers, you usually put a comma, so you make sure it's at 35, right? So it'd be dimethyl. Right? You get 2 methyls, right? So 1 at 3, 1 at 5, no name, and then you put the main chain at the end, right? So notice how, even though this is a di, it starts with D, right? We keep it there because all we care about is ethyl and methyl. Okay. If you have a di here, it indicates you have 2 methyl groups. You have to put 2 numbers, even if they're the same number. Okay. So like that. So the ethyl comes out here. So does this make sense, right? We have So we have a main chain that's 9. Okay. We have 2 methyl groups, right? 1 at carbon 3, right? 1 at carbon 5, right? And then we have an ethyl group, right? Where's that hanging out? Hanging out at carbon 4. Not too bad. So that should make sense, right? So there's your name. Okay. So we have right? So when you draw the structure, right, it's usually easier to go backwards. Okay, so you draw the main chain first, right? So you can go out and put a condensed structure in here, something else. I'm just going to go ahead and do the skeletal structure, 2, 4, 6, 8, 10, right? So you put the dots in. Dots are fine. And if you want to put the 10 dots in a row, that's fine. Right? So, okay, so 2 methyl, right? So if we're gonna number these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have a methyl group hanging off of carbon 1, right? Okay, so that's the main chain, right? So we have a 1 carbon piece coming off of there. And then at carbon 4, okay, we have a 2 propyl group, right? So propyl group, right, it's 3 carbons long, right? Okay, right? 1, 2, 3. But instead of being connected to the main chain through carbon 1, what we're saying is it's connected through carbon 2. Okay, so there we go. So there you go. So with that, so there's your structure. So Okay, so for Newman projections, right? So here's what we're going to do: draw the and it says calculate the steric energy for the steric, and then draw the a corresponding eclipse configuration. Doesn't matter. There's going to be several the molecule, and calculate the steric energy for it. Okay, so if you want to have a little chart, right, you're going to need to know these, memorize these values. I'm not going to give you the values for you. Right, so you have H, right, H, CH3, and then CH3, CH3. Okay, so if you have a staggered, right, versus an eclipsed version, right, so for staggered, each one of these is worth 0. Okay, but this one's worth 3.8. Okay. And for eclipse, this is equal, this cause, in the eclipse form, this is worth 4, right, this is worth 6, and that's worth 11. Okay, so what you do is you just go around, right, we're going to look at these interactions here. Okay, so this one here, it's an eclipse, or we're in the staggered, right? So methyl is 3.8. This one's worth 0. This one's worth 0, 0, 3.8, 3.8. Right? So it'd be so this becomes 3.8, 0.8. Just add them up. 3.8. Right? So it'd be let's see, 12. It'd be 11.4 kilojoules per mole. Okay. Now, to draw the eclipsed configuration, okay, what I usually do, you can do it either way. I usually keep the front where it is, so CH3, H, CH3, right, and then I rotate these guys 60 degrees, either clockwise or counterclockwise. It doesn't matter, right? So it'd be CH3. This one would come down here. CH3, and then this guy would come over here, like that. Okay. So for this one, right, methyl, eclipsed, right, that's worth 11. Methyl hydrogen's worth 6, right, and then the other one's worth, this one, methyl hydrogen, is worth 6, right. So it'd be 11 plus 6 plus 6, right. So 23 kilojoules per mole. There you go. Now, there's a bunch of different ways that you could rotate this. There's 3 different ways that you could rotate it. I just need 1. Okay, as long as you calculate it, that's fine. So there you go. You need to memorize these values here. So. Okay, so for these, what we're going to do is we're going to say, right, for these values here, okay, predicting which way it goes, right? So the value, right, the reaction always wants to go towards the higher pKa acid, right? So in this case, right, so 20 to 15, the reaction is actually going to want to go that way, okay? So the reverse is the one that you want to go, right? So if you had, right, 2 to 4, right, on this one, right, it would go forward, right? No worries, right? It's always going to, the reaction is always going to proceed to the higher pKa value. So in this case, it's over here, so the reaction is going to prefer to be reversed. Here, it's going up, right, 2 to 4. So even though the numbers, it's just relative, right? So even though this is 20 and 15, right, you're going up, so this one's going to go forward. That's it. So, and I'm going to give you these numbers here. So you just need to know how to use them. Okay, so for acid-base reactions, right, I'm going to do one of two things, right? So there's 2 different types of ways that I can show this. Either I can give you the reaction, ask what is acting like the acid, right? Circle the acid, right? Or I can give it to you like, that's one set of reactions, one question. The other question is going to be like this, where I tell you what the acid and base is and then draw the products. Okay, I'm not going to, I know in the homework we combine them, but you can at least go look up what that is. Here, you're not going to have that luxury, right? So here we go. So, right, so remember, acids give up, and going from here to here give up an H, okay, and stuff like that. So you look at C, and the bases grab it, right? So acting like an acid, right? So going from here to here, right? This has lost this H here, going from here to here. This guy has picked it up, right? So here's that H, right? So this one here is acting. This is acting like the acid. Okay. go from here. Okay, so to draw the products, right? So what does a base do? It comes in here and it grabs the hydrogen, right? So like that. So again, right? So you lose not only an H but a plus charge, right? So this becomes negative, right? Because in neutral you lose a plus charge, so it becomes negative, right? And this one goes like this, right? It gains not only an H but a plus charge, so that plus charge knocks out that negative sign, so it goes here. So here's your products. Okay, so it's either going to be predict the product, figure out which one's the acid, or it's going to be predict the product where I tell you what the acid and the base are. So there you go. Okay, so for isomers. Okay, so here you go. So isomers just mean that they have this formula, but they have different names, basically, if you were to name them, right? So for here, I give you this, but I also say that it must contain an alcohol group. Okay, so here you go. So an alcohol group, right, is an OH, right? So you could put it here, right? So so then you fill in the hydrogens, right? So H2, H2, CH3, right? You got to make sure that you got the right formula, right? 2, 4, 7, 8 hydrogens, right? 1 oxygen, 3 oxygens, or 3 carbons. Right? Make sure it works. Okay. The other thing that you can do, now you got to just move these pieces around, right? So what you could do, say, is move this OH to right here. Right there, right? So this would be a alcohol in the 1 position. This would be an alcohol in the 2 position. Right? And again, you fill in the necessary hydrogens, right? Make sure it all makes sense, right? 3, 6, 7, 8, right? 8 hydrogens. So there you go. These are your 2. But the important thing is, right, you got to keep that alcohol. If I tell you there's an alcohol group, you got to make sure that the alcohol is there. Okay. Now, this one here, you have to be careful, right? Because you don't want to draw it like this. Say, well, I want to put that CH3 group here. Lop this off and put it there, right? Because that is still, notice how the main chain is still 3 carbons long. That is just this rewritten. So these are the same compound. Okay, so it's still going to be just these 2. Okay. Okay, so functional groups. Okay, so these I really like. Okay, so here I'm going to give you some actual drug names or whatever. So here you go. So this one here, this is Lyrica. So this is for pain. So with that, so usually what you want to do is you want to look for anything that has a double bond or triple bond, and anything that's a non-carbon. Okay, so you just start at one end, right? So I'm not going to have you circle alkanes, cycloalkanes, which are sort of carbons that sort of come back. I'll show you one in a minute. And benzene rings. Okay, so benzene rings. So these are benzenes, right? So they're a hexagon, right, with alternating double, single, double, single, double, single. Okay, that's a very special group. You don't need those. If you can't pick those out, then I've certainly failed you. So like that. So those don't need to be marked, but everything else does. Okay, now a double bond that's in a cyclohexane, right? So it's within a ring. That's fair game as long as it's not part of this benzene group. Okay, so like that. So here you go, right? So here, this is an obvious one, right? You sort of go one side, maybe come up here, right? So there's no single bonds. You don't have to worry about this. That's just telling you the stereochemistry. So this hydrogen is actually coming out at you. This bond is going away from you in the plane of and these guys are within the plane. Okay, so this one here, it's a nitrogen, right? But what you always have to look for is the presence of the C double bond O. Okay, there's no C double bond O next to it, so that makes this one an amine. Okay, so now if you keep going down here, notice how there's C double bond O here. Whenever you see that, you ding, 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 stuff like that. So right here, what you have is a carbon on one side and an OH on the other, right? So that makes this not an alcohol and a ketone. This makes this a carboxylic acid. Okay, so there you go. Okay, so down here, notice this here, how the carbons sort of cycle back on each other. So that would be a cycloalkane, right? Because it's just single bonds. Now, if there's a double bond in here, then you'd have to circle it, unless it's a benzene, right? Unless it's a benzene like this, where you don't. But this one here, there's no, right? So with that, so for here, you have that C double bond O, okay? So, but you have a carbon on one side and a carbon on the other, right? So that makes this a ketone. This one here, right? That one right there, right? You don't have a C double bond O next to it, right? So that makes this an alcohol. Okay. And if you go down these chains, right? So here you have a carbon-carbon double bond, right? So that's an alkene, right? It's not part of a benzene. It's just a regular alkene. Here again, you have an OH, right? And next to it is not a C double bond O, so that makes this an alcohol. Okay, just go down the end of this ring, and we're done, right? So these are all just alkanes. If you go down here, right? So that's just denoting stereochemistry that's going away. So it's going along here. This one is, again, C double bond O, so you have to be really careful what's going on with it. One side is a carbon, the other side is an O carbon, right? So that's different from a carboxylic acid. This is an ester group. Okay. So this is cytotec, by the way, misoprostol. I don't know. It's an NSAID, so it's a non-steroidal anti-inflammatory, something like that. So it's also used for labor induction, something like that. So in pregnancy. Okay, so here we go. Now, this is another way that you can draw the benzene. So these are benzenes here. This is just how the drawing program threw them out, something like that. So, okay, so this is Acupril. So this is used for hypertension, something like that. So here we go. So this one here, right, this is benzene. We don't have to cite this sort of cycloalkane here. We don't need to, but we are interested in this nitrogen. And notice how there is a C double bond O next to it. Okay, that makes this an amide. Not an amine, right? An amine would have only carbons or hydrogens next to it. Okay, so like that. So same goes with this. Notice that there's an OH here, but there's a C double bond O right there. Right, so that makes this a carboxylic acid. Okay, for here, right? So we have a nitrogen, a C on one side and a C on the other. Notice how this one there is a C double bond O, but it's too far away. Right, you would need to be right next to it. Okay, so this is actually a amine. Okay, this one here, there is a C double bond O, C on one side, and OC on the other. Okay, so this is your ester. Okay, so this is Acupril. Right, so at the end down here, there's a benzene. You don't need to mark that. Okay. Okay, so for this one here, there's benzene, benzene, benzene here. Now, these two here, okay, those are actually a little more complicated. It's actually part of an aromatic, stuff like that. Normally, for what you guys see, if there's a double bond like this, that's not part of a benzene, circle it. Okay, but in here, I'm not going to circle it for some technical reasons, right? Stuff like that. But if you go over here, right, so this is atorvastatin. This is Lipitor. It's used for cholesterol lowering. Okay, so you can start on this side, right? So there's a nitrogen, right? But there's a C double bond O next to it. So that is an amide. Okay, here we go. Right, you have a nitrogen, right, with a carbons on, with just carbons on it, not C double bond O. So this is an amine. Okay. Okay, now for here, notice that there's a fluorine there. So you can either call that just a fluorine or a fluoro, or you could call it a halide, or you could call it a halogen. I don't care. Just to indicate what that is. Okay. So here we have an OH, right? That just has carbons on either side of it. Okay, so it's an alcohol. Again, same with this one. OH, right? Just C's on either side of it. So alcohol. But this one here, there's an OH, right? But there's a C double bond O next to it. So that is a carboxylic acid. There you go. That's Lipitor. Okay. So for this one, this is Symbicort. So with that, so so notice that there's this 6-membered, 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 5-membered right there. That's a steroid structure there. Okay, so there's a whole bunch of stuff going on in here. Okay, it's kind of a fun molecule. So you just start at the one side and go to the other. So these, I should point out that these guys here, remember these are just these heavy lines here, that's just stereochemistry, how things are positioned in space. Okay, so this one here, right, CO10, there's a carbon on one side, carbon on the other. Right, so this is a ketone. This one up here, there's this, right, carbon-carbon double bond. It's not part of a benzene ring, right? So that is an alkene. Right, this one here is also an alkene as well, right? Notice how I said benzenes are single, double, right? So even though it's a cyclohexane with 2 double bonds in it, right, you need 3 with that alternating pattern, right? This is a cyclohexane. You don't need to worry about that. Cyclohexane or cycloalkane, don't have to worry about that. But this one here you do, right? But it has carbons on either side, so that is an alcohol. Okay. So going around, these are just hydrogens. That's a methyl group. Hydrogen. Here we go. So, right. So an oxygen, right, with carbons on either side. Okay. So that is an ether. Okay. These guys on this side here, again, this is an ether, right? Because carbons on both sides, right? So it's an ether. If you really want to be technical, it's actually an acetal, but for right now, I'd be happy if you just wrote ether. Stuff like that. So for this guy here, it is a C double bond O, but there's carbons on either side. Notice that, yes, there is an OH, but it's too far away, right? That OH would need to be right here to be carboxylic acid. So this is a ketone. And then that makes this, because there's just a C double bond O attached to it, that makes this an alcohol. Okay, there's a whole lot going on in symbol court, but that's what we got. 2 ethers, alcohol, ketone, alcohol, 2 alkenes right here, and a ketone. So there you go. Okay, so this is physoteridine. It's Toviaz. It's used for overactive bladder, right? So these guys here with the circle in them, those are benzenes. So you don't have to worry about that. Okay, so here we go. So we have a C double bond O, right? So we have a carbon on one side, right? O carbon on the other. It doesn't matter if this is part of the benzene. It's just a carbon, right? So this is an ester. Benzene. So here we go. So OH, right? So it's just attached to a regular carbon, right? So this is an alcohol. Okay. This one, if you get on here, that's benzene. Come down here. Nitrogen, right? So it just has regular carbons attached to it. No C double bond O. So this is an amine. So there you go. Okay, I think we get 2 more sets. 3 more molecules. Okay. So this is nexium. So this is S-imeprazole, right? And actually, the reason why it's that is the stereochemistry there. Okay. Okay. So here we go. So this one here, right? So C on one side, C on the other, right? So this is an ether. Okay. This is a benzene. Okay. This here. That there, notice that there's carbons on either side, right? So that's an amine. Okay, same goes with this one. There's carbons on both sides, and then a hydrogen. That's fine. There's not a C double bond O. That's the important part. So this is also an amine. Okay, that guy there, right? The S double bond O, right? That's a sulfoxide. Okay, and here, there you go there. Right? This overall thing is a benzene, but there is a amine in here, okay? Because it's just carbon-carbon. Right? And here again, an alcohol, or excuse me, an oxygen with carbons on either side. This is an ether. Okay, so there you go. Nexium. Next one is Cymbalta duloxetine. It's used for depression. Okay, so here we go. So this is actually, I know this doesn't look like it, but that's actually this one here is actually a benzene. These two are actually 2 benzene groups, right? So that's how this would actually work. So you can sort of think of that as being that down there. So these are actually 2 benzene. This one right here, right? So there's carbons on either side, right? So this is an ether. Okay. This one right here, right? There's a sulfur with carbons on either side, so that makes this a sulfide. The sulfur version of an ether. right? And this one right here, right? There's just carbon, carbon, hydrogen, right? No C double bond O, so that's an amine. So Cymbalta. It's pretty easy, pretty not a whole lot going on. Something like that. Lastly, we have Flovent. Again, notice this is a steroid. It's very similar to the other steroid that we had, right? So you have these chains here. That's what make, right there. So the like that. But again, right? So this here is just carbons on either side, right? So this is a ketone. Right? These guys here, they're double bonds that aren't part of a benzene. So these are both alkenes. Right? These two, that one and that one, right? You could call these fluorines, or you could call them halides, or I'll take halogens. Okay, I don't care, right? Fluorine. Okay, the OH here, right? There's just carbons on either side, no C double bond O, right? So no C double bond O here, right? So like that. So this is an alcohol. Right, so these are just hydrogen and methyl. Okay, so here we go. So C double bond O, right? O, C, right? So this is an ester. Okay, this one here, C double bond, you got a C on one side and an S on the other. So this is the sulfur version of an ester. Lots of times when you see sulfur, you think thi. So this is a thioester. Okay, this is the sulfur version of an ester, so a thioester, so sulfur version of an ester. And again, you have this fluorine, or halide, or halogen. I don't care. Halogen. So there you go. Very similar to the other one, like that. So there we go. So good luck. We'll finish this up on Monday.